asymptote of a polynomial curve is defined to be the straight line to which the curve tends to or merges to as x tends to infinite. In a sense, we may say that f(x) merges to the asymptote y equal to mx plus c as x tends to infinity. Here, when we have asymptotes parallel to x axis, obviously we have this straight line to which the curve tends to, given by parallel to x axis means y equal to some constant, isn't it so? And similarly parallel to y axis asymptote is given by x equal to some other constant k1. And when we say we have oblique asymptote, we have y equal to mx plus c as the form to which the curve tends to as x tends to infinity. Now, let us write a polynomial curve of nth degree, the general form of it. We may write the polynomial curve of nth degree as polynomial curve of nth degree. We write it as a0 x to the power n plus a1 x to the power n minus 1 y plus a2 x to the power n minus 2 y square and dot 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 a n y to the power n. Similarly, the next set of terms with degrees n minus 1 may be written as b0 x to the power n minus 1 plus b1 x to the power n minus 2y plus b2 x to the power n minus 3 y square and so on with bn minus 1 y to the power n minus 1, so on. And we have the linear term as, let us write it as c0x plus c1y and then the constant term d equal to 0. One can easily apprehend or understand the idea of writing a polynomial curve of nth degree like this. Here we have in the first bracket all the terms which has power n. See, this is x to the power n and x to the power n minus 1 into y. So, the actual power of the term is nth power. X to the n minus 2 is multiplied with y square and we have clustered all the terms which has nth degree in terms of the variables x and y in the first bracket. Similarly, all the terms having degree n minus 1th order we have clustered it in the second bracket and so on. So, this is our linear term and this is our constant term. So, degree of variable is 1 here and degree of variable is 0 here. Now, for simplicity we may take that d is 0 and this is equal to 0. That means all the curves which passes through origin, This is for a simplicity, we take it without any loss of generality. Now, the utility of writing the polynomial curve of nth degree in this way is that if we take x to the power n common from the first term, we have obviously a0 plus a1y by x, isn't it so, plus a2y by x whole square plus dot 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 we have an y by x whole to the power n. So, we may write this term as a polynomial in terms of y by x. Y by x is the variable, we assume it, and we replace y by x by m, because we have assumed that y equal to mx plus c is the asymptote. Since this is the asymptote, we know that y by x tends to m as x tends to infinity. This is the basic idea of asymptote, isn't it so? Since the oblique asymptote has the equation y equal to mx plus c, we assume that y by x tends to m as x tends to infinity, because if we divide it by y by x, here it becomes m and here it becomes c by x. As x tends to infinity, c by x becomes 0, and we have y by x tending to m as x tends to infinity, and that is why we have written this as like this, and we replace this term as a polynomial of y by x of degree n, and we replace this term as phi suffix n of y by x, isn't it so? Similarly, the next term, if we take out x to the power n minus 1, from each term we have phi of n minus 1 of y by x, isn't it so? Because the term starts from b0 and then it is b1 y by x, b2 y by x whole square, and ends at bn minus 1 by y by x whole to the power n minus 1. Similarly, if we take x common from this term, we would have phi 1 y by x, that is the linear term involving y by x. Okay, we have all the other terms written here. Now, we divide throughout by x to the power n and take the limit of this as x tends to infinity, and obviously we have this, isn't it so? We may write an extra term here which we have skipped here, and the last term will be 1 by, we have divided with x to the power n, so it will be y by 1 by x to the power n minus 1 phi 1 y by x, isn't it so? So, it is visible in the board, I hope. This term, this is 0 equal to 0, and obviously we don't need any of these terms because x tends to infinity, and from this expression we can easily write that as x tends to infinity, we have y by x tending to m. So, this equal to 0 implies actually phi n m equal to 0, and this m denotes the gradient of the required asymptote, isn't it? So, if we have a polynomial of nth degree, then we can simply put y by x equal to m in the highest degree terms bracketed within, and this m phi n m equal to 0, the roots of this equation gives us all the possible required asymptotes. See that a polynomial of nth degree can have at most n roots, so we may have exactly n asymptotes for a polynomial curve of nth degree, and we may have less than that. We may have 1, we may have 2, because other roots may be complex, isn't it so? So, phi n m represents the equation from which we can get the asymptote of all the polynomial curves of nth degree. Now, let us try to find out the C part of the asymptote, isn't it so? Now, if you can remember, you may write the equation like this, that phi n m plus 1 by x phi n minus 1 m, isn't it so, plus 1 by x square phi n minus 2 m and other terms. before we have taken the limit of x tends to infinity. And since so, we should write logically phi n y by x, isn't it so? Phi n minus 1 y by x and phi n minus 2 y by x. The last term was the linear term, which is, you may remember, the last term was 1 by x to the power n minus 1 phi 1 y by x. Since we have chosen the curve which passes through origin and we do not have any constant term here, if we would have a constant term here, the constant term will be written as d by or any constant by x to the power n, since we have divided it, all the terms with x to the power n only. Now see that from here we have y by x equal to m plus c by x, simple. So if we now take the limit as x tends to infinity, we get that phi n m is equal to 0, giving the value of gradients of all the required asymptotes. And to find the c, we just use a very unique technique. What is this? We apply Taylor's expansion to these terms, and for that matter we replace this y by x with this. So it becomes phi n y by x is m plus c by x, phi n minus 1, this is also m plus c by x, 1 by x square phi n minus 2, and this is also m plus c by x, dot dot dot. We are not interested about the other terms for a purpose. Now just concentrate about these three terms. Why? I am trying to explain. And we do Taylor series expansion. Taylor series expansion. Why? Because as x tends to infinity, we know that 1 by x is very small term, and if we take Taylor series expansion and then actually take the limit, since we have replaced it with this, we will obviously take the limit of this, of all these terms. Okay, I am not writing the other terms, because in all the other terms 1 by x cube, 1 by x to the power 4 and dot dot, they can easily be avoided as x is very large. Now what about the Taylor series expansion of this term? Let us remember that Taylor series expansion of f of x plus h, where h is very small, is written as fx plus h f prime x plus h square by factorial 2 f double prime x dot dot dot. There is the correction term Rn, which involves the nth derivative of f at the point x plus theta h. I am not going into that detail. Let us forget about this Rn, because since this h is very small, we just use these three terms. Just as we skipped all the terms with power more than square, since x is very small, so 1 by x cube will be much smaller than compared to these two terms. So we don't keep those terms, we just keep the terms up to square. So the Taylor series expansion comes out to be this only, and we are replacing all these terms with this, assuming that m stands for x here and c by x stands for h here. So what do we get? We get phi n m plus, it is c by x phi n prime m, isn't it so? Just remember that if f of x plus h, it would have been fx plus h f prime x plus h square by factorial 2, that is c square by x square 1 by factorial 2 phi n double prime m, isn't it so? Similarly, from the second term, what do we get? We get 1 by x and then we have phi n minus 1m. Let us keep a bracket here. The Taylor series expansion of this, we have c by x phi n minus 1 prime m plus c square by x square into 1 by factorial 2 phi n minus 1 double prime m, and so on. We are just keeping these three terms only. What about this term? Similarly, we have 1 by x square into phi n minus 2m plus c by x phi n minus 2 prime m plus, I am not writing this term, you can write it. Now just see that phi nm is 0, we know that as we take the limit. We are taking limit term by term. So this term cancels out. And now we can easily multiply with this x, and it is advisable obviously. So it becomes this only, and it becomes this only. And what about this? This x cancels out, but this x remain. And what about this? It becomes 1 by x, isn't it so? And then we take the limit of x tends to infinity. Actually, while taking the limit, we see that phi nm is actually 0, so we cancels out, and then we multiply with an x and take the limit as x tends to infinity. See that all these terms are 0, so we have only this and this, isn't it so? Just take a good look. While multiplying by x and then taking the limit, we have left out with these two terms only. So after taking the limit from this relation, we have c phi n prime m plus phi n minus 1m equal to 0, because all these other terms are becoming 0 here. Wherever 1 by x is there, we have 0. So we have left out with, after taking the limit, only these two terms, this one and this one, and they become 0. So c phi n prime m plus phi n minus 1m becomes 0, giving us the value of this, isn't it so? And we have the equation of asymptote. So it's clear. Now there is another point to be noted. What is the point? The point is that we may have repeated root, cube root, isn't it so? Phi n m, we have assumed that it has a single root. It may have a double root, isn't it so? This has n roots, m1, m2, dot 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 mn. First we have said that it may so happen that all these roots are not real, then we don't have n real asymptotes or n real state lines. But it may have at most n asymptotes for a polynomial curve of nth degree. Now one realize that it may so happen that it has repeated root m1, m1 and then m2, isn't it so? So these two are repeated root. So in case of repeated root, we know that not only phi nm is 0, phi n prime m is also 0, isn't it so? Whenever m is a repeated root, we have this relation. Now look back to the expansion here. What we have done is that phi nm plus Taylor series expansion, c by x phi n prime m plus c square by factorial 2x square, factorial 2 means actually 2, phi n double prime m, isn't it so? Plus it turns out to be 1 by x. Then what about the Taylor series expansion of this term? Let us keep a bracket here. So it is phi n minus 1 m plus, then we have similarly c by x phi n minus 1 prime m and c square by 2x square phi n minus 1 double prime m. Okay, and similar three terms of from the polynomial of